Hello everyone. Let us discuss SN1 and SN2 reactions of this compound. As we discussed in previous classes, I'll discuss in brief. SN1 reaction is a formation of a carbocation, right? Tertiary, more reactive, then secondary, then primary, then methyl halide. In SN2 reaction, as we discussed, is a single step reaction, right? SN2, SN1, right? Two step reaction. SN2, single step reaction. And what else we discussed? Here racemization takes place. That I will discuss later in stereochemistry. Here inversion of configuration takes place. We will discuss in detail in next class. And carbocation, tertiary is more reactive, primary, secondary. Here primary is more reactive, then secondary, next is tertiary. And first highly reactive is methyl halides, right? Methyl halide is more reactive than primary, then secondary and tertiary in case of SN2 reaction mechanism. Keep this in your mind. Now, consider these compounds. First compound is primary. Why is primary? Here this bromine atom attached to the carbon atom containing two hydrogen atom and one more benzene ring C6H5, right? So it is a primary. Second one, carbon containing one halide, the halogen atom, that is bromine containing two more carbon atoms. Hence first one is primary, second one is secondary, and third one is again secondary. Two hydrogen atoms are replaced. Here all three hydrogen atoms are replaced by alkyl groups. Here it is benzene, two benzene and one methyl group. Hence it is a tertiary, right? Now let us discuss reactivity in SN1 mechanism. Which one will undergo SN1 reaction in faster rate? Which one will undergo SN2 reaction in a faster rate? Okay. For SN1 reaction, tertiary alkyl halide or tertiary carbocations will undergo reaction in faster rate or greater, right? Hence, first compound will undergo SN1 reaction in faster rate. Hence, reactivity order is C6H5, C6H5 and CH3 and Br. It will undergo SN1 reaction in greater rate. After that, as we know, secondary. Here there are two secondary compounds are there. Now which one will undergo SN1 reaction in faster rate? Out of two, which one will stabilize? Both will stabilize by resonance, right? This here two benzene rings are there. To this carbon, two benzene rings are attached. Hence this carbocation formed will stabilize by resonance. There are two benzene rings are there. But here, first step carbocation formation, that carbocation formed will stabilize either by resonance, both resonance and by inductive effect, positive inductive effect. As we know, resonance effect is greater compared to inductive effect, right? Hence, this compound will undergo SN1 reaction in faster rate. It prefers a SN1 reaction. Hope it is clear, because two benzene rings are attached, hence carbocation formed is resonance stabilized. Here carbocations formed is resonance stabilized and inductive effect, stabilized by inductive effect, but resonance stabilization is greater compared to inductive effect stabilization. Hence C6H5 and here C6H5H and Br, secondary carbocation. Next again this secondary carbocation hydrogen C6H5 is nothing but benzene ring and methyl group and bromine atom, and last one is primary, right? Primary C6H5 and CH2Br. This is order of reactivity in case of a SN1 reaction. Now what about SN2 reaction? So lesser the bulkier group, greater will be the reactivity, right, in SN2 reaction. Hence primary will react faster in SN2 reaction, as we know. So that C6H5 CH2Br, it is primary compound, will undergo SN2 reaction. Next is secondary. Secondary means again we have to see bulkier groups. Here C6H5 C6H5, right, and in next compound it is C6H5 and CH3Br. Now which one will undergo SN2 reaction faster rate? First compound is primary, next is C6H5 CH3 and Br. Why? Because here C6H5 and C6H5 both are bulkier groups. Hence reactivity, and here C6H5 is bulkier, compared to that CH3 is not much bulkier. Hence reactivity is CH, here it is C6H5 and next is CH3 and Br. Hope it is clear for you. Here reactivity because of, there it is because of carbocation formed is resonance stabilized, but here it is if bulkier group is present, reactivity will be decreases. Benzene rings are more bulkier compared to methyl, hence this secondary compound will react faster or prefers SN2 reaction in greater way. Next is again secondary compound C6H5 C6H5 and here it is this compound hydrogen and here bromine, and last one is a tertiary, that is C6H5 C6H5 CH3 and Br, right? It is very less. Reactivity order SN1 reaction due to tertiary carbocation is stabilized here by resonance and inductive effect, but here it is both resonance, here one is resonance, one is inductive effect. Here it is primary carbocation is of course reactive, it is stabilized directly attached to CH2 group, stabilized by inductive effect. But what happens here SN2 reaction? If lesser the bulkier group, greater will be the reaction. Hence primary will react faster rate. Next reacts a secondary, in that lesser the bulkier group, more will be the reaction. Hence carbon atom attached to C6H5 and CH3 reacts. Reactivity is greater compared to C6H5 and C6H5. Last is tertiary carbocation or tertiary alkyl halide. Let us discuss one more example, that is isomers of bromobutane. That is CH3, CH2, 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 Br. Right? It is 1, 2, 3, 4 bromine. Right? It is bromobutane. Now, bromobutane, I will write isomers of this compound. This compound CH3, CH2, one isomer. Again I will write one more isomer, that is CH3, CH3, here it is CH2, 1, 2, 3, 4, 5, Br. One more isomer, right, like this. In these compounds, first one is a primary alkyl carbon containing halogen atom is directly attached to one more carbon atom, and here this compound, so it is attached to two more carbon atoms, hence it is a secondary. And third compound is again it is primary, and third is tertiary. 1, 2, 3, 4. So 4 carbon atoms, 3, 6, 7, 8, 9. Correct. Now let us discuss about SN1 reaction mechanism. As we know, tertiary carbocation or alkyl halide reacts faster by SN1 reaction mechanism, hence CH3 tertiary butyl bromide, we discussed the mechanism, will react greater way in SN1 reaction. After that secondary compound is there, that is 1, 2, 3, 4 CH2, CH, Br and CH3 secondary, and next is primary. But here there are two primary compounds are there. Which one will react first? Here carbocation, it will ionize, then we'll get a CH2 plus as a carbocation. This carbocation will stabilize by only one alkyl group, that is CH3, CH2, CH2, inductive effect. But here this carbocation is stabilized by CH3CH, this group, and also this one, right? It is stabilized by greater inductive effect compared to this. Hence, this compound react in greater way compared to simple primary halobromobutane. Here it is, name of this compound is 1-bromo-2-methyl propane. Here it is 1-bromobutane, right? Bromobutane. Now reactivity is next is CH3. Hope it is clear for you. Due to greater inductive effect of this group, carbocation formed is stabilized in greater way. Next is primary CH3, CH2, 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 Br, right? It is about SN1 reaction. Now about SN2 reaction. As we know, if there is lesser the bulkier group, greater will be the reaction. Here tertiary reactivity is less. Next is secondary, and highest reactivity we can observe there in primary. Hence first is CH3, CH2, 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 Br will undergo SN2 reaction. After that, just ulta of this, CH3 reverse order, CH, CH3, CH2, Br, and next is a secondary compound, CH3, CH2, CH, Br, and CH3, and last is a tertiary, CH3, and here also CH3, CH3, and Br. So due to here tertiary carbocation is more stable, but here it is primary one, hence it is more reactive. It is about SN1 and SN2 reaction mechanism. Very, very important concept. Now we'll discuss about stereochemical aspects of chemistry or nucleophilic substitution reaction. After that, we'll discuss about stereochemical aspects of SN1 and SN2 reaction. Chemical aspects of nucleophilic substitution reaction. Okay. Here we should know some terms. Here some specific terms are used while discussing stereochemistry. Now we already know what is stereochemistry, stereoisomers, right? Compounds may have same molecular formula but differ in the spatial arrangement of atoms. We know in butanol or propanol, any compound will be having same molecular formula, but their spatial arrangement will be different. For example, one will be, we represent that by wedged line or a solid line. That represents a spatial arrangement of atoms, right? Compounds may have same molecular formula, 2 or more, but differ in the spatial arrangement of atoms. Then those compounds will show optical isomers. These concepts we discussed last year. Now, in stereochemical aspects, first we'll discuss few terms, that is optical activity, then polarimeter, okay, and plane polarized light. Okay. This three-dimensional arrangement of atoms gives different properties to the compounds. That we'll discuss in this concept. When we pass normal light is scattered in different direction. When we pass this normal light through Nicol prism, okay, it's a kind of prism invented by Nicol. Then here these light rays are vibrating in different direction, different planes. On passing through Nicol prism, we will get a plane polarized light like this, right? Which will vibrate in a single plane. When we pass this plane, this is about a plane polarized light, right? It will vibrate in a single plane. Direction will be single. Here it is different directional. when we pass this plane polarized light through solution of optically active organic compound. Okay, when we pass this plane polarized light through organic compound, that is optically active. I will tell what is optical activity. This organic compound rotates this plane polarized light either left side or right side. Left side or right side. That is, it will rotate this compound, rotate this plane polarized light towards right side or to left side. Okay. Then this phenomenon is called optical activity, and only few compounds can rotate this plane polarized light to right side or left side. Such compounds are called optically active compounds. Only some compounds can rotate plane polarized light to left side or right side, hence those compounds are called optically active compounds, and this phenomenon totally is called optical activity. Okay. Now, if this compound rotates plane polarized light to right side, okay, right side, then are called dextrorotatory. Dextro, that is a Greek term. Dextro means right. If our organic compound rotates plane polarized light to right side, plane polarized light to right side, then are called dextrorotatory. Okay. If our compound rotates plane polarized light to left side, then are called levorotatory. First one is dextro and second one is levorotatory. Levo means left side, or we can represent this by letter D and levorotatory by L. We can easily remember levo, L, levorotatory. Dextrorotatory means D. And if I take clock, okay, right side we call this as a clockwise, right, that is right side, and left side we call it as anti-clockwise, right. Hence dextrorotatory is also called clockwise direction, rotation clockwise. If organic compound rotates plane polarized light right or clockwise, it is called clockwise, and it's called anti-clockwise. Okay, anti-clock and clockwise directional. Or I will take scale, your normal scale. Here it is 0, right. Right side it will be +1, +2, +3, etc. And left side it will be -1, -2, -3, etc. Right. And hence for right side direction or dextrorotatory, we can represent dextrorotatory as a plus and levorotatory as a minus. Okay, this is about rotation of plane polarized light in presence of optically active compounds. Hope it is clear for you. And this angle of rotation, here it is, if I take middle plane polarized light, it rotates right side or left side. This angle of rotation is measured by a instrument. that instrument is called a polarimeter. Okay, instrument which measures the angle of rotation of dextrorotatory or levorotatory, and that instrument is called a polarimeter. Okay, now it is when when normal light passed through a Nicol prism, then you will get a plane polarized light. When plane polarized light passes through optically active compound, it rotates either right side or a left side. Right side is called dextro, left side is levo, or positive, negative, clockwise, anti-clockwise, or plus or minus. And this is called optical activity. The compound which shows these optical activities are called optically active compound, and this angle of rotation is measured by instrument is called a polarimeter, right? And this isomers D, okay, this mixture of these isomers are called isomerism. D or L is called optical isomerism. Optical isomerism. Okay, one compound will show here when we pass plane polarized light, one compound will show of two isomers, one will show levorotatory, another isomer show dextrorotatory. This is called, if it shows two isomers shows D or L are called optical isomers. One compound may show dextrorotatory, another may show levorotatory, are called optical isomers, and that phenomenon is called optical isomerism. Let us discuss about optically active compounds, right? I already said only few compounds, certain compounds can rotate this plane polarized light. What is the condition for to show optical activity? Let us discuss about this topic. Carbon tetrahedral, I'll take tetrahedral carbon, 3-dimensional tetrahedral carbon. If it contain, that is valence is 4, hence if it is contain 4 different groups, tetrahedral carbon attached to 3 different groups in 3-dimensional, 3 different groups, then are called, remember, asymmetric carbon. That is important. Asymmetric carbon or chiral carbon. If carbon attached to tetrahedral carbon attached to 4 different groups, I'll take again carbon A, here it is B or C, D. Okay, if it is attached to 4 different groups, then are called asymmetric carbon or chiral carbon. Only these compounds will show optical activity. Just remember what is asymmetric carbon or chiral carbon. Now, what is chirality? A chiral carbon, if carbon is attached to same groups, okay, here AA, these two are of same groups, hence this kind is called, this type of carbon is called symmetric carbon, symmetric or a chiral carbon. Okay, thank you.